Good morning, everybody.
Morning.
Good morning.
Okay, so in the previous class, we looked at the properties of systems, and then we looked at one of the representation of discrete time system, which is the difference equation. Now we say the difference equation, this is general format for it. And depending on the expression that we have, we can identify two types of filters. One is the FIR filter, and one is the IR filter. Now, if you look at the FIR filter, what characterizes an FIR filter? It's fine. The impulse response is finite in length. But why? How do we look at an expression of a difference equation and say, oh, this is an FIR filter versus an IR filter? If it does not depend on previous or future outputs, then it's an FIR filter. Make sense? The output only depends on the input. It does not depend on the output. The IR filter, the output depends on the input and on the output. Make sense? So you can see how we have recursion or feedback in the IR filter. The output depends on previous or future outputs. Here, the output only depends on the input. And as a result of that, as we will see in more details, the FIR filter will have a finite impulse response, whereas the IR filter will have an infinite impulse response. The FIR filter is always stable since I have finite number of terms. If I add them according to the stability criteria, they're going to be finite. And we can find the output of the FIR and the IR can depend on previous or future input. That will determine whether it is causal or not causal. Okay, so given an FIR filter, how do we find the impulse response of the FIR filter? So let's find the impulse response, and we'll finish that, and then we'll start a new topic, but we'll just go back to this for a second. So let's say we have an FIR filter that has this difference equation. Let's represent this FIR filter using a block diagram. So what we can do, we can say this is equal x of n. If I take x of n, multiply it by b0, and then I'm going to take x of n, I'm going to delay it. What do I get here? X of n minus 1. I'm going to multiply it by b1. Then I'm going to take it, I'm going to delay it. I'm going to get x of n minus 2. I'm going to multiply it by b2, and so on and so forth. And then I'm going to add these together. I'm going to add this. I'm going to add this all the way to get my y of n. Does that make sense? This is a representation of this equation. X of n multiplied by b0. I delay x of n. I'm going to get x of n minus 1 multiplied by b1. Delay it. X of n minus 2 multiplied by b2. And I add all these together. I'm going to get y of n. Make sense, everybody? Again, we'll see this in more details later. But for the time being, if I want to find the impulse response of this system, how do I find the impulse response? How do we find the impulse response? We apply an impulse, isn't it? We apply an impulse at the input, and then we see what the output is. If I applied an impulse at the input, what is the output going to be equal to? I have an impulse, delta of n. When n is 0, what am I going to have? A delta here, multiplied by t0. What is y of n going to equal to? B0, yes. Y of n is going to equal to B0 multiplied by delta of n. Agree? Everybody? A delta multiplied by B0, the output is B0 multiplied by delta. After 1 unit delay, what is going to happen to this delta? There's going to be a 1 here, isn't it? And then what is the output going to be? B1 multiplied by delta of n minus 1. One unit later, B2 multiplied by delta of n minus 2, and so on and so forth. Does that make sense? So at n equal to 0, at the first instant in time, I have the impulse at 0. When n is equal to 1, this impulse is going to be at 1. Then this impulse is going to be at 2. So when n is 0, I'm going to get an impulse multiplied by B0. When n is 1, impulse multiplied by B1, and so on and so forth. And therefore, what is the impulse response of this filter? This output. This output is the impulse response. Why? Because it's the output when I applied an impulse. So therefore, h of n is equal to B0 delta of n plus B1 delta of n minus 1 plus B2 delta of n minus 2, etc., etc. And therefore, h of n is going to look something like this. At 0, it is a B0. At 1, B1. At 2, B2, etc. Is that clear? Any confusion? Yes, no? Clear? Okay. Now, the last thing we're going to discuss here is how do we solve these difference equations? So let's take an example and see how we solve these difference equations. Of course, this is one method of solving the difference equations. So let's say we have y of n equal 3 over 4, y of n minus 1 over 8, y of n minus 2, plus 2x of n, plus 6x of n minus 1. What kind of filter is this? IIR. Why? Because it depends on the output. Because I have these two terms. This is an IIR filter. Okay. So in order to solve for the output, we need to know the input, x of n. Let's say we applied a unit step. And also, I need the initial conditions. So I need y at -1. It's given to equal 4, and y at -2, and it is equal to -8. Why do I have these two initial conditions?
The first two terms.
Because if I were to calculate y of 0, it's going to depend on y of -1 and y of -2. So I know what I need to know what these are. I'm calculating the output when n is greater than or equal to 0. When I calculate when n is equal to 0, I'm going to need y of -1, y of -2. What is the why don't I have initial conditions for x of n? Because it's the input. Because we know what the input is. The input is known at all times. Okay. So one way we can solve these equations, one very simple, is to iterate over all the values of n. So I'm going to come.
I have a question. So, but if x is at 0, I don't get the last term.
What is x of n minus 1? If x of n is equal to a unit step, 0.
Okay. All right.
We know, like, at any time, we know what x of n is. We do not need, because it's known. The output is the one that is unknown. So we're going to solve for y of n by iterating over values of n. So I'm going to start and say, okay, when n is equal to 0, y at 0 is going to equal to 3 over 4, y at negative 1, minus 1 over 8, y at negative 2, plus 2 multiplied by x of 0, plus 6 multiplied by x of negative 1. What is this going to equal to? 3 over 4 multiplied by y of negative 1, which is 4, minus 1 over 8 multiplied by negative 8, plus 2 multiplied by x of 0 is going to be a 2, plus 6 multiplied x of negative 1, which is a 0. What is this value going to equal to? A 3, 8, plus 1, plus 2, which is going to equal to a 6. Together? Then we're going to go to the next iteration. Y at 1 is going to equal to 3 over 4, y of 0, minus 1 over 8, y at negative 1, plus 2 x of 1, plus 6 x of 0. Where do I get y of 0 from? From 1 that we just calculated. Make sense? Y at 0 is going to equal to 6, so we have 3 over 4 multiplied by 6, minus 1 over 8 multiplied by y of negative 1, plus 2 times x of 1, which is a 2, plus 6 times x of 0, which is a 6. Make sense? Everybody? And we can iterate till we find, like, till whatever index we want to calculate the output. What is another method that we can use to calculate the output? Another method we can use to calculate the output. If I want to calculate using the convolution, what do I have to do? I have to calculate h of n from this difference equation, and I know the input x of n. I can convolve them to get the output. Make sense? Okay. Any questions? Questions? Okay. So this is just to finish up what we did in the previous class. What we're going to do in this class, what we're going to be doing today, is we're going to be talking about discrete time Fourier transform. Now what we're going to be doing is this. We're going to be covering this discrete time Fourier transform in more details later. However, we're going to be using it before we cover it fully. So we're going to introduce it, and hopefully, since we're going to introduce it early on, we'll become more familiar with it because we're going to see it over and over again. Make sense? Now a warning, we're going to be doing lots of math in this in today's class. So don't get distracted, try to stay with the class. Now there are fundamental things that we're going to take from all this work. That hopefully the math we can always do but there is also fundamental concept that we have to understand after we cover this. Everybody's ready? Your energy 100%? Okay. So before we start, so what we're going to be talking about, we're going to be talking about Fourier transform. We're going to be talking about discrete time Fourier transform. We're going to be talking about discrete Fourier transform. So not only one transform, three transforms. Okay. So just recall a few formulas that we're going to be needing in the development that we're going to be doing. First one, if I integrate from negative infinity to infinity, delta of t dt, what is this equal to? 1. Similarly, if I take the summation from negative infinity to infinity of delta of n, what is this going to equal to? 1. This, I have just an impulse when n is equal to 0. Make sense? And therefore, the summation is going to be just that impulse, which is equal to a 1. Make sense, everybody? Okay. If I take a function, or a signal x of t, multiplied by delta of t minus tau, what is this going to equal to?
X of t convolved with?
Okay, what else?
X of t minus tau?
X of t minus tau, that's correct. That's part of the answer. We have, oh, not x of t minus tau. Keep going. I'm going to show you what to do. I mean, it looks overwhelming, isn't it? But in reality, it's straightforward. What is this? I have a signal, x of t. I'm multiplying this x of t with an impulse at tau. Make sense? That's what I'm doing. I'm taking x of t, multiplying it with delta of t minus tau. Delta of t minus tau is just an impulse at tau. Now, when I multiply these, remember, what does this impulse look like? We can imagine it as being a rectangle, isn't it? A rectangle, the width is going to 0, the magnitude is going to infinity, but the area is equal to 1. When I multiply this rectangle by x of t, what value of x of t is going to become?
Whatever's at tau.
Whatever is at tau, yes. So this x of tau here is going to get multiplied by that impulse. Make sense? So it's going to scale that impulse. I'm going to get x of tau delta of t minus tau. So the result of this multiplication is going to be just this impulse scaled by x of tau. Anybody not convinced? Everybody convinced? 100%? 100%. No doubt whatsoever. A function, again, just imagine this for a second, it's a rectangle. Multiply it by this. This rectangle, the magnitude is going to be just scaled by x of tau. And therefore, it's going to equal to x of tau, and the impulse is still at tau. Good? Okay. Again, if anything is not confusing, if anything is confusing, tell me. We'll do it again till you feel like, okay, I see it. Okay. Similarly, we can do something in discrete time. If I have x of n multiplied by delta of n minus m, what is this going to equal to? Without looking at this, what is this going to equal to?
X of n
X of m, very good. What else?
times the delta.
Times the delta. Very good. Again, something similar. I have x of n, I have a sequence, x of n, and then I multiply it with an impulse that happens to be at m. This what used to be a magnitude of 1. Now it's going to multiply whatever x of m, whatever value x of m at this point is. It's going to scale this impulse. Sounds good? Everybody? Okay. This is the warm-up before we start the lecture. Okay. Another formula. What is x of t convolved with delta of t minus tau? And you should know the answer to this. Anybody want to try? Or because I said you should know the answer to this, now nobody wants to take a risk of being wrong. Okay, let me correct. You can know the answer to this if you want. How about this? What if we imagine this as a system, x of t, and then I apply to it an impulse at tau? What happens if I apply to calculate the output? What is the output? It's going to be the convolution of this impulse with this x of t, isn't it? We used to call this h of t, but I can call it x of t. What is the output going to be? Okay. Let's simplify it, although if I have a h of t and I applied an impulse at 0, what do I get at the output? H of t. Very good. Now if I applied this impulse not at 0, I applied it the next day at tau, what do I get?
H of t minus tau.
H of t minus tau. Thank you. Agree? Because it's time invariant. Okay. Now what if I come here and instead of calling it h of t, I'm going to call it x of t. Can I? What do I get at the output? I got x of t. I'm going to get x of t minus tau. Agree? So what is the output? What is the result of this convolution? X of t minus tau. Okay. Similarly, if I take x of n convolved with delta of n minus m, what is this going to equal to? X of n minus m. Following the same logic. Together? Again, this means convolution. I should have said that. Hopefully everybody understood. Okay. Another formula that you're going to need. What is the integration from negative infinity to infinity? X of t delta of t minus tau dt. Who wants to make a guess? Okay, let's see if we can figure it out. So I have a signal x of t. Good? What is it? Okay. We have x of t, and I have an impulse. Now I'm going to represent this impulse as a rectangle, even though we know it's not a rectangle, but we can, just for visualizing it, it's a rectangle that has an area of 1. Good? What is the area of that rectangle? 1. This rectangle is happening at tau. Now, if I multiply these two and take the integration, what is the integration going to equal to? This is happening at t, sorry.
X of t is 1.
Excellent.
It's the area under the curve, right?
Yeah. If I multiply this this rectangle is going to get scaled by whatever x at t. Then if I take the integration of it, it's going to be just x of t. With me? When I multiply these together, this is going to become now x of t. The magnitude is going to be scaled by x of t. And therefore, if I take the area, originally the area of this was 1. But I scaled it by x of t, and it's going to become x of t.
Capital T, right?
Capital T, yes. Everybody together? Agreement? Okay. Again, you don't have to memorize. You should not memorize any of these. You should always visualize them. Just do a small drawing. It should be hopefully easy to figure it out. Okay, if I take the summation from k equal negative infinity, x of k, delta of n minus k, similar to the continuous time, is going to equal to x of n. Exact same logic. Good? Again, the index here is k. So this is going to be non-zero only when k is equal to n. It's going to be scaled by x of n. Make sense? What are these two properties called? Excellent. Sifting property. Why is it called sifting property? Why? Because I sifted from all this signal the value at this x of t. Make sense? That's why it's called sifting property. Okay. Okay. Let's start our discrete time Fourier transform discussion with the Fourier transform. What is the expression for the Fourier transform? The Fourier transform of a signal x of t. Anybody memorize what x of omega gonna equal to? The integration of x of t e to negative j omega t dt. What does this look like from things that we've seen before? Laplace transform. How is this different than Laplace transform? What is Laplace transform compared to this? Laplace was e to s e. Agree? But what is s equal to? Sigma plus j omega. So if I evaluate Laplace along the j omega axis, I'm going to get the Fourier transform. What is the inverse Fourier transform? I can take the Fourier transform and calculate the inverse. It's equal to 1 over 2 pi, the integration from negative infinity to infinity, x of j omega e to j omega t d omega. These two expressions are the definition of the Laplace transform. What does the Laplace transform tell us? If I have a signal, the frequency content of that signal, the spectrum of that signal. The Fourier transform. I said Laplace. The Fourier transform. Although, the Fourier is related to the Laplace. The Fourier transform will give us the frequency content of the signal. Okay. Now we are already familiar with the Fourier transform. We know everything about the properties and the spectrum and all that. What we are interested in, of course, I'm going to make the assumption that nobody ever heard of Fourier transform. Am I wrong? I am wrong. You heard of it. But I'm going to make the assumption
From
that,
dynamic systems.
yeah, we're going to make the assumption it's a new transform. So the point I'm trying to make, if you feel like, oh, wow, he's assuming we know Fourier transform, I hardly heard of Fourier transform, you're fine. I'm not going to assume you know it. So stay with me. Okay. Now what we're going to do is the following. We're going to introduce the Fourier transform. We're going to introduce the discrete time Fourier transform, and then we'll do examples. Make sense? And hopefully you'll see after a few examples, you feel like, okay, I got it. Like it will become clear what all these transforms do. Okay. Now, what we want is we're not interested in the continuous time signals, but rather we are interested in discrete time signals. So if I have a discrete time signal x of n, we want to define a transform similar to the continuous time transform. What are we going to call this transform? Discrete time Fourier transform. Discrete time Fourier transform. And the way we're going to define this transform is by associating with x of n the continuous time impulse train What does all this mean? Here's the following. We have Fourier transform. Now we have x of n. I want to be able somehow to use this Fourier transform to calculate the frequency content of x of n. Make sense? But I can't. This is a discrete time signal. So what I'm going to do, I'm going to create a signal, a continuous time signal from this x of n using an impulse train. What that means, I'm going to create a continuous time signal that is x of t that is going to equal to the summation from n equal negative infinity to infinity, x of n delta of t minus n multiplied by t. Does that make sense? What is it we're doing here? You're giving me x of n. You tell me, oh, I have this x of n signal. I have a file here that has your audio recording, and it has these values. 50, 66, 31, 19, 20, 15, etc. This is x of n. So I'll tell you, okay, take these values and just represent them like this. At 0, have an impulse, and the value of this impulse is 50. At 1, at t, take an impulse that has a value of 66. At 3, take an impulse this is 2t, that has a value of 31. At 3t, take an impulse that has a value of 19, and so on and so forth. What is this signal? X of t. Together? Anybody confused, or everybody with me? This is a continuous time signal. What is the label here? T. Make sense? This is a continuous time signal. This is different than this signal. What's the difference between them? They look the same, aren't they? And that's why, like, if you don't pay attention, you're going to think, oh, this is the same. But they are not. This is a discrete time signal. This is a continuous time signal.
Time.
Sorry?
Time. I guess time is.
Yes, this is time. Therefore, it's a continuous time signal. This is index. Make sense? So what I've done, I've taken these indices, I generated a continuous time signal that looks like this from them. Good? Everybody? Okay. And then I said, okay, you have a discrete time signal that looks like this. You're going to calculate the Fourier transform for it. Generate this x of t. Now you have a continuous time signal. Use the Fourier transform to calculate the spectrum of this. Make sense? Everybody following what we're doing? We started with x of n, which is discrete. I want to know the spectrum of it. We said, okay, take this x of n, use an impulse train to represent it as a continuous time signal. Then use Fourier transform to calculate the spectrum of this. So let's do that. So what we're going to do is we're going to take the Fourier transform of x of t. What is the Fourier transform of x of t? It's going to give me x of j omega, which is going to equal the integration from negative infinity to infinity. X of t, which is the summation from n equal negative infinity to infinity. X of n, delta of t minus n multiplied by t, e to negative j omega t dt. Agreement? Everybody? So this is the Fourier transform of that impulse train signal that we generated from the discrete time signal. Okay. Now we can write this. We have integration and summation. I can swap them. I can write this as the summation from negative infinity to infinity. I can take x of n. It's not a function of time. And then the integration from negative infinity to infinity, e to negative j omega t multiplied by delta of t minus nt dt. What is this going to equal to? Based on what we've done in the recall, we can write this as the summation from n equal negative infinity to infinity, x of n. What is this integration going to equal to?
It's E, right?
It's going to be whatever this function is
Yes.
at nt. Remember, it's the shifting property.
There's one.
Whatever this function, evaluated at n multiplied by t multiplied by 1. Make sense? So this is going to equal e to negative j omega multiplied by n multiplied by t. Again, this comes directly from here. Integration x of t delta of t minus t is x of t. Delta of t minus nt is going to equal x at nt. If this is exponential, exponential evaluated at nt. Are we together, everybody? Okay. So therefore, we can express this as a function of e to j omega t. So we can write this as x as a function of e to j omega t is equal to the summation from n equal negative infinity to infinity x of n e to negative j omega n multiplied by t. So just instead of writing this in terms of j omega, we can express it as x of e to j omega t. Okay, but if you recall, we defined the discrete time frequency omega. What was the discrete time frequency omega equal to? W multiplied by t. You recall that, everybody? The first or second class, we defined omega as equal to W multiplied by t. So therefore, if I substitute for W, I can write this as e to j omega equal the summation from n equal negative infinity to infinity x of n e to negative j omega multiplied by n. And this is how we define the discrete time Fourier transform. X of t, x as a function of e to j omega is equal to summation x of n e to negative j omega multiplied by n. We call this the discrete time Fourier transform. Together? Okay. Now, if you look at this expression, we know that e to j omega is equal to cosine omega plus j sine omega. And therefore, we know that cosine omega, sine omega, they're periodic. And therefore, e to j omega is also periodic. What is the period equal to? 2 pi. That means if I have any phase e to j omega 1 is the same as e to j omega 1 plus 2 pi. Why? Because this is equal e to j omega 1 multiplied by e to j 2 pi. What is e to j 2 pi equal to? 1. E to j 2 pi is going to equal cosine 2 pi, which is 1, plus j sine 2 pi, which is 0. This is equal to 1. So anytime I add 2 pi to any omega, I'm getting back the same omega. I'm getting back exponent of e to j any omega is going to equal e to j, that j omega plus any integer multiple of 2 pi. Is that clear, everybody? E to j omega is periodic. So therefore, if I look at my expression here, since I have e to j omega in it, x of e to j omega has a period that is equal to 2 pi. If I add a 2 pi to this omega, this is going to give me the same value. If I add 4 pi to that omega, it's going to give me the same value. So therefore, x of e to j omega is periodic, and it has a period that is equal to 2 pi. Any questions? Okay. we're going to define the inverse of x of e to j omega as equal to x of n, which is going to equal to 1 over 2 pi, the integration from 0 to 2 pi, x of e to j omega multiplied by n d omega. So if I have x of omega and I want to calculate the inverse, I'm going to calculate the inverse x of n. I'll use this expression to calculate the inverse discrete time Fourier transform. Again, I realize all this is new and it's overwhelming, so just just understand what we're covering, and hopefully by the end of the semester, all of it will come together, it becomes more clear. Okay, but this discrete time Fourier, we're going to be using it even before we get to covering it in detail, so that's why we're introducing it now, so when we use it, at least it looks familiar. So let's look at some properties of this discrete time Fourier transform. The first property that we said, it is periodic, and it has a period that is equal to 2 pi. Another property is that x of e to j omega is complex. It has magnitude, which we call x of e to j omega, and it has phase, which is x of e to j omega. Does that make sense, everybody? So when we calculate x of e to j omega, in general, it's going to be complex. So it has a magnitude, it has a phase. So when we plot them, we plot the magnitude, we plot the phase. So keep that in mind. Okay. Other properties, if I have x of n convolved with h of n, if I take the discrete time Fourier transform of it, this is going to equal to x of e to j omega multiplied by h of e to j omega. And this is the convolution property. Where have we seen something similar to this? With continuous time. Multiplication, convolution in the time domain is multiplication in the frequency domain. The same thing applies here. Okay. If I take a signal x of n and delay it by d samples, it's going to have a Fourier transform, discrete time Fourier transform, that is e to negative j omega multiplied by n sub d x of e to j omega. This is the time shift property. If I shift the signal in the time domain, what is the impact of that shift? A phase in the frequency domain. Okay. Another property, x of n multiplied by w of n. If I multiply two signals in the time domain, in the frequency domain, this is going to equal to 1 over 2 pi x of e to j omega convolved with w of e to j omega. We call this modulation property. Multiplication in the time domain is convolution in the frequency finally, the discrete time Fourier transform exists only if x of n is stable. Okay.
What's stable mean here?
Similar to how we define the stability. The summation of magnitude of x of n does not go to infinity. Okay. So we have all these properties. Let's do some examples. The first example, we're going to find the Fourier transform of the rectangular pulse below. I have a rectangular pulse that looks something like this. Now this is continuous time. So what we're going to do, we're going to do this in continuous time. Then we're going to sample this pulse. Then we're going to calculate the discrete time Fourier transform. Then we're going to look at both and try to see the similarity and differences between them. Together? So what we're going to do, so let me give you a preview of what we're going to do. This is what I'm going to do. We're going to take this pulse. We're going to calculate the Fourier transform for it. Good? Then I'm going to take samples of this pulse. So I'm going to come here and say, oh, what happens if this is a discrete time signal that looks like this? I'm going to calculate the spectrum for it. Then I'm going to compare this spectrum and this spectrum and understand what each one is telling me. Does that make sense, everybody? So we're going to start this. We're going to calculate the spectrum for it. Then we're going to have a signal like this. We're going to calculate the spectrum for it. Then we're going to put them together and say, oh, okay. Oh, they're related, more related than we thought. Okay. So let's start with this pulse. How do we find the Fourier transform for this pulse? We use the formula. X of w equal the integration from negative infinity to infinity, x of t e to negative j omega t dt. Why do we usually start with this pulse? Because it's simple. You can see we can do the integration very easily. What is this going to equal to? Integration from negative t0 to t0, x of t is equal to 1, e to negative j omega t dt. What is this integration equal to? No, not that simple. This is exponential. I mean, this is not a constant, it's a function of time. So it's going to be e to negative j omega t divided by negative j omega, agree? And the limit from t naught to t naught. What is this going to equal to if I substitute the limits of the integration? 1 over j omega e to j omega t0 minus e to negative j omega t0. Anybody not happy? Everybody's happy? What did I do? I flipped it. Yeah, because we have a negative sign, I flip the limits or you can do it in 2 steps. So you can do it in 1 step. Okay, so what do we have here? How can we simplify this? Anybody?
What is formula?
1. What is e to j omega minus e to negative j omega?
It's like a cinch or something.
It's a sine. A sine. E to jx minus e to negative jx over 2j is equal to sine x. But what do I need to make it a sine? I need this. Well, I have a j. I just need a 2. So I can multiply and divide by 2. Multiplied by 2 divided by 2. And then I'm going to get a 2 multiplied by sine omega multiplied by t0 divided by omega. Agree, everybody? Where it came from? Are we done? We're done, but we can even make it look even better. We can multiply by t0 and divide by t0. Then I'm going to get sine omega t0 divided by omega t0. See it? T0 with t0 cancel. I'll get this one. But now I have the same argument here and here. What do we call this function? Sinc. Okay. So great. So we calculated the Fourier transform for our first function. And I imagine, even if you have not seen, if you've seen this before, now that we've done it together, you're going to always remember what the Fourier transform of a rectangular pulse like this. And what is it going to be? A sinc. This is omega. What is the magnitude at t equal to 0? Two multiplied by 0. At 0, 0 over 0, L'Hopital's rule, omega t 0 cancels. I'm going to have t 0. Is that clear, everybody? Where is this frequency? How do I find this frequency? Well, we want this argument to be equal to a pi, isn't it? We want omega t0 to equal to a pi. So what is omega going to equal to? Pi over t0. Agree? So this is pi over t0. Similarly, this is going to be 2 pi over t0, 3 pi over t0, etc. Okay, so this is the spectrum of a rectangular pulse. Now this sinc keeps going from negative infinity to infinity, but what happens to it? It gets smaller and smaller and smaller. Make sense? Now one thing, just keep in mind, this is time limited, isn't it? It only exists finite time. What happens to it in the frequency? It becomes band unlimited. Anytime limited signal is going to be band unlimited signal. Okay.
Sorry, what is the band unlimited mean?
like it goes from negative infinity to infinity. It's not limited in a band. The spectrum goes from negative infinity all the way to infinity. Here it is limited, time limited. Here it's frequency unlimited or band unlimited. Okay. Now, of course, looking at this, looking at this pulse, what this spectrum tells you, if you inherit that pulse is made up of frequencies, very low frequencies here. As you increase the frequency, the contribution of the frequency becomes less and less and less. The contribution of these frequencies are like this, contribution of this frequency, etc., etc. Make sense? Now, of course, looking at this signal, you can predict that the spectrum makes sense. Why? Because this signal is not changing, it's just a constant. So you expect the spectrum to be very low frequency. There's no high frequency changes. Why do we need all these high frequencies? To make that transition here. How does it gonna go from this value to this value, jump like this? It's gonna require all these high frequencies. Make sense? Okay. Now this is the easy part. Now what we're gonna do, I'm gonna take that signal. Of course, I'm kidding about being the easy part. Just trying to get you to put more energy. Now what I want to do, I want to come to that spectrum that we plotted, or that signal that we plotted the spectrum for. And I'm going to do this. I'm going to come and take samples of it. So I'm going to write x of n. X of n looks something like this. What is the similarity between this signal and the signal we just calculated the Fourier transform for?
Discrete.
This is discrete. Yes, if I went to that signal, the one we just did, and I took samples from it, I came to this signal and I took samples from it. I took a sample here, a sample here, a sample here, sample here, sample here, sample here, sample, sample, sample. What do I get? I'm going to get this signal. So you see how they're related? This could have come from that signal. And if I calculate how many n's I'm using to sample, I can calculate the sampling time, how often I'm taking a sample. Make sense? Okay, so now what we want to do, I want to calculate the discrete term Fourier transform. Okay, easy. Discrete time Fourier transform, e to j omega, or x of omega. What is it equal to? According to the formula, it's equal to the summation from n equal negative infinity to infinity, x of n e to negative j omega multiplied by n. Agree? This is the definition. Now, all what we're going to do till the end of the class is just calculate this. We're going to go through details. That's why it's going to look like messy, but it's straightforward. What is this summation going to equal to based on x of n? Negative n1 to n1. What is x of n? Oh, I don't have a value. Here's a value. 1. 1 multiplied by e to negative j omega n. That's it. This is the discrete time Fourier transform of this sequence. But this expression is not very useful. isn't it? So we're going to try to massage it to see if we can get some meaning out of it. So I'm going to go to my summation tables, and my summation tables tell me that if you have a summation from n1 to n2 of a to k, this is going to equal a to n1 minus a to n2 plus 1 divided by 1 minus a. So we're going to come back and say, okay, let's use that expression on this summation. What is this going to equal to? E to negative j omega multiplied by negative n1 minus e to negative j omega multiplied by n1 plus 1 divided by 1 minus e to negative j omega. Agree? Everybody? Just plug in the values in this summation. A, I can write this as e to negative j multiplied by omega to the n. So A is equal to e to negative j omega.
Question. Is the plus one in the subscript or not?
There is this one.
Yeah. Plus one.
Omega multiplied by n1 plus 1.
So the n1 plus one, not the one.
No, n1 plus 1 because it's n2 plus 1.
Okay.
It's coming from here.
Just making sure it's not in the subscript.
Yeah, it's fine. Yeah, n1 is above the subscript. Okay. So again, all what we're going to do is massage this expression, try to get something meaningful out of it. So this is, we can take e to j omega n1 as a common factor, because here is negative, negative, it can become positive. So I can take e to j omega 1 outside. I'm going to get 1 minus e to negative j omega multiplied by 2 n1 plus 1. Agree? If we multiply it, j omega with negative 2j omega, I'm going to end up with negative j omega.
Where did the denominator go?
I'm going to write it.
Okay.
And the denominator is still 1 minus e to negative j omega. Okay. Then what I'm going to do, I'm going to do this. I'm going to write e to j omega n1 Again, this math is long and tedious, and it is not what we're trying to do, but nevertheless we'll do it one time so you know how it is calculated. But in general, what matters to us more is the concept of what this all means. I can write the 1 as e to negative j multiplied by e to positive j. Multiplying these together will give me a 1. I'm going to write the second term as e to negative j omega 2n1 plus 1 over 2 multiplied by e to negative j omega 2n1 plus 1 over 2. Everybody knows what we've done? Yes, no?
So do you have to do something to the denominator now?
Well, I'm going to add the denominator. Just the numerator. 1, I can write it as e to jx multiplied by e to negative gx. So this adds up. If I multiply them, these add up to 1. Here, I took the phase, I split it in 2, I divided it by half. So this plus this, when I multiply these exponentials, they add up together. 1 half plus 1 half becomes a 1. It will give me this one. Make sense? Everybody? Okay. What do we have in the denominator? We're going to go something similar. The 1, I'm going to write it as e to j omega over 2 multiplied by e to j omega over 2. What is the result of this multiplication? A 1. And then I have e to negative j omega. I'm going to write it as negative j omega over 2 multiplied by e to negative j omega over 2. What is the result of that? E to negative j omega. Okay. Then what we're going to do is we're going to take e to j omega n1. I'm going to take e to negative j omega n1 plus 1 over 2 as a common factor. So I'm going to take e to negative j omega multiplied by 2n1 plus 1 over 2 as a common factor. And in the denominator, I'm going to take e to negative j omega over 2 as a common factor. And what I'm going to have left with is e to j omega 2n1 plus 1 over 2 minus e to negative j omega 2n1 plus 1 over 2. And in the denominator, I'm going to get e to j omega over 2 minus e to negative j omega over 2. Any objection? All what we've done we've taken this factor out as a common factor. I've taken this factor out as a common factor, this factor out as a common factor. Make sense? Okay. So then we can express this as equal e to j omega n1 multiplied by e to negative j omega n1 multiplied by e to negative j omega over 2 multiplied by e to j omega over 2. Where are all these terms coming from? E to j omega 2n over 2 is going to give me this term. This term is this term. Agree? And then I have j omega over 2 is going to give me this one. And finally, I have this one. I took it to the denominator. It's going to become j omega over 2. See that? Negative j omega times 2n1 over 2 is negative j omega n1. Negative j omega times 1 over 2, negative j omega times 1 over 2. I had in the denominator e to negative j omega. I'm going to take it to the numerator. It becomes e to j omega 2. Everything is counted for. Who wants to be in charge of missing terms? Okay, sine. Oh. Now if I look at this, what does this look like? A sine. What does this look like? A sine. What does it need? A 2j and 2j. So I'm going to divide by 2j and divide by 2j. I did not change anything. But now over 2j, the whole thing over 2j. Yes? So this over 2j, this over 2j. So if I do that, I'm going to get a sine of omega multiplied by 2n1 plus 1 over 2 divided by sine omega over 2. And all these terms that multiply are going to cancel out. So what I'm going to end up with is sine omega over 2 multiplied by 2n1 plus 1 over sine omega over 2. This cancels this, this cancels this. Any objection? Is this straightforward? Okay, we'll stop here. Next class, we'll look at the plot of this. We compare it to the Fourier transform, and we'll create some intuition into the relationship between the two. Thank you, everybody.